Hello, welcome to another capacity chemistry video. This one's all about electrophilic addition. Now, first question. What is electrophilic and what is addition? Now, philic, you've seen that in nucleophilic, and philic is likes, and electro sounds like electron. Electrons are negative, so it's electron or negative, something that likes negatives and you're just adding it on. That's electrophilic addition. Now here we've got an alkene. I'm sure you guys can all name this alkene. It's ethene. And what's this got to do with electrophilic addition? This thing has got a really electron rich area here in this double bond. Now if you don't know about pi bonds yet, go and Google them, make some notes on them, and then come back to this. Now in this mechanism we're going to start off really simply. It's called electrophilic addition, one more time. And what we're going to do is we're going to add bromine to it. Now you guys will have seen that before in real life. Hopefully you've seen the test for alkenes. You add bromine water to an alkene and you see that it changes from orange to clear colourless. Now why? Here's why. Take a look at this mechanism. So there's our bromine next to our ethene molecule. The electrons in this bromine are directly in the middle because the difference in electronegativity is 0. So the electrons are equally shared. As the bromine molecule approaches this ethene molecule, this area of electrons will repel the electrons from the middle of this bond closer to this Br here. So what we're left with is partial charges, a delta minus and a delta plus. Now that delta plus and that delta minus allow this double bond to come over here and form a bond with that Br, which then forces these electrons over here. A bit clear, over here we've got an arrow going next to this bromine because it's forming a bond with it, and over here from the middle of this bond to that second bromine. This puts us in the position where we've got this intermediate now. We've got this bromine that's joined on to this organic molecule. We've got this carbon that's got a plus charge on it, and we've got a bromide ion over here with a lone pair of electrons. So what's going to happen here? We've got this from the middle of the lone pair coming and bonding with that, and then we'll finish it off. And you can all name that 1,2-dibromoethane. The thing I didn't point out about this intermediate is it's called a carbocation. Carbocation. Now cations are positive ions, so there's the positive charge and it's on a carbon, so carbocation. These are things that you're going to have to be used to now as well. This mini whiteboard's got our carbocations on it. There's 3 different types that you need to know. This one's a primary one, a secondary one, and a tertiary one. And what have they all got on them? They've all got a carbocation, so a carbon that's positively charged, and they've also got different numbers of R groups. What's an R group? An R group is any alkyl chain, so you could have stuff like a methyl group, which is a CH3, an ethyl, CH3, CH2, propyls, butyls, anything longer than that as well. An alkyl chain is what we're talking about when we mention an R group. Now when we talk about primary carbocations, we say that they've got 1 R group attached to them. When we talk about secondary carbocations, they've got 2 R groups attached. One's an R and one's an R dash. Now the dash means that they're not the same. They could be the same, they don't have to be the same, and that's why we put it as R dashed. And a tertiary carbocation, carbocation, has got 3 R groups on it. Now what you need to know about stability, and a tertiary carbocation is the most stable, and a primary carbocation is the least stable. What does this mean? This means that as an intermediate, this one will hang around for the longest, and this one won't hang around for very long at all. Why? Why, I hear you ask? It's all because of this thing, the positive inductive effect. Now what does that mean? That means that this carbon with its positive charge, it can pull in the electrons from all of these R's. So these R's, we could call them methyl groups if we wanted to, or ethyl groups. Let's put them in. There's a CH3, there's a C2H5, and let's put in a CH3 as well. So we got 2 CH3s and 1 C2H5. Now what will happen is, this carbon's positive charge, it will pull the electrons, the clouds of electrons, towards itself, to make that charge a little bit more spread out, to make the effect of that charge less. So this one will hang around for the longest. This one has got less carbons that it's bonded to, these alkyl chains, and because it's got less carbons that it's bonded to, the charge is spread out over a smaller area. And then this one, the charge is spread out over an even smaller area, so it's less stable. It's more positive dense. Let's have a go at this. Butanene plus HBr. If you've got time, pause the video, take a look, see if you can do it yourself. But now I'm going to draw it out as well. So we start with butanene. Now I'm always going to draw it out like this. The double bond is my main focus, and I've drawn everything else around it nice and simply. We're going to add HBr to it. Now there's my HBr. HBr is polar, delta minus, delta plus. Why? Because of the difference in electronegativity. We've got this double bond that's going to see this molecule here, this electrophile. It's going to come for it. So there we go, that is that bond being formed. So we've got an arrow from the middle of the carbon-carbon double bond coming next to that H, and the electrons from here will go to that Br. We then form a carbocation. Right, this is the part where students often get stuck and they're like, sir, which one does it form? Does the H join on here, or does the H join on here? Now this is where I need you guys to take a look at this mini whiteboard again and tell me which one do you think it will be. So we've got 2 ways to do it. Let's do it both ways. The H can join on there, and that will mean that there is a plus charge on this carbon. Or, we'll draw it out again. The H can join on to this carbon, and then we're left with a plus on this carbon. Now your job here is to see the difference in the two. Let's start with the bottom one. This carbocation, it's got 1H, 2H and 1R group. That means it's a primary carbocation. And this one at the top, you've got 1H, 1R group, 2R groups, and because you've got 2R groups, this one's secondary. if we come back to this thing again, we've got a primary one and we've got a secondary one. The secondary is more stable because tertiary is most stable and primary is least stable. So because secondary is more stable than primary, what we say is that we'll get more of this carbocation formed, which means that our final product, I haven't finished off the curly arrows, but our final product, this product versus this product, we'll get lots more of this one. And so the way we describe it is, this is the major product and this one is the minor product. And those are two keywords you need to be able to use. This is a secondary carbocation, more stable than a primary, so this one is our major product. This is a primary carbocation, so this whole thing will be our minor product. And I think that's where I'm going to stop. If you've got any questions or comments, please add them in the comment section below. Have a go at some exam questions on this. Good luck.